Welcome everyone to the problem solving session of the thermodynamics course from NPTEL. I am Pradeev E. I am one of the TA for this course. Today I will solve some problems using heat engine and heat pump concepts, and then I will move on to problems with the entropy concept. So first problem is on the screen. A heat engine is used to drive a heat pump. The heat transfers from the heat engine and from the heat pump are used to heat the water circulating through the radiators of a building. The efficiency of the heat engine is 27% and the COP of the heat pump is 4. Evaluate the ratio of the heat transfer to the circulating water to the heat transfer to the heat engine. So we have a heat engine. So we have a heat engine and a heat pump. Entire work from the heat engine is transferred to the heat pump, and a heat engine has is in contact with the two thermal bodies, TH1 for high temperature and TL1 for as low temperature reservoir. I write Q1 as heat transferred from the high temperature reservoir, and Q2 is the heat rejected by the heat engine to the low temperature reservoir, and W is the work that is generated by the heat engine. Similarly, the heat pump is in contact with two thermal reservoirs, TH2 and TL2, and Q3 and Q4 are the heat transferred to the high temperature reservoir and heat absorbed from the low temperature reservoir. Now it is said that for the heat in the building, the heat from the engine and the heat from the heat pump are used to heat the circulating water. So that means Q3 and Q4, Q2 and Q3 are used to heat the building, and we need to find the ratio of this Q2 plus Q3 divided by Q1. So Q1 is the heat that is given to the heat engine. That is what mentioned here. So now I will start by writing the expression for the known terms. Now we know Q1 by TH1 is equal to Q2 by TL2. Similarly, Q3 by TH2 is equal to Q4 by TL2. We are given the efficiency. So efficiency of the heat engine is equal to 27%. So that is 1 minus I would write work output divided by Q in. So here work output is from energy balance, we know that it is Q1 minus Q2 divided by Q1. So this is 1 minus Q2 by Q1. Similarly, the COP of the refrigeration system is 4, and that is desired output, which is Q3 for the heat pump divided by the work input. And again this Q3 divided by work input, I can write it as Q3 minus Q4, or from the heat engine I know that it is Q1 minus Q2. Both the work are same for the heat engine and the heat pump. So for the COP expression I can write it as Q3 by Q1 minus Q2. Now this is 4, and I can solve this. Finally, we need to know this Q2 plus Q3 by Q1. I can write Q2 in terms of Q1. So from efficiency, this is 0. So 0.27 is equal to 1 minus Q2 by Q1. So this means Q2 by Q1 is equal to 1 minus 0.27, which is 0.73. So that means Q2 is equal to 0.73 of Q1. And writing that expression in this COP equation, so 4 is equal to Q3 divided by Q1 minus 0.73 of Q1. So this is Q3 divided by 0.27 Q1. I need Q3 by Q4, so which implies Q3 by Q1 is equal to 4 into 0.27. So this is 1.08. Similarly, I can calculate Q2 by Q1. I have already calculated Q2 by Q1 is equal to 0.73. So Q2 plus Q3 by Q1 is Q2 by Q1 plus Q3 by Q1. Q2 by Q1 is 0.73 and this is 1.08. So it is 1.81. So we have calculated the ratio that was asked in the question. If you have any questions, you can ask now. Then I will move on to the next problem. The next problem, we have a reversible heat engine, heat engines A and B that are arranged in series. A rejecting heat directly to B. Engine A receives 200 kilojoules at a temperature of 421 degrees Celsius from a hot source. So we have a heat engine A. This is rejecting heat directly to, we say it is a thermal reservoir, and then from the thermal reservoir it goes to heat engine B. So this gets heat from a high temperature reservoir of 421 degrees Celsius. So that is 694 Kelvin, and this heat Q1 is I would say this is T1 is equal to, and this Q1 is given as 200 kilojoules, and I would write the work output of the heat engine 1 as WA and work output of heat engine 2 as WB from a hot source, while the engine B is in communication with the cold sink at a temperature of 4.4 degrees Celsius. So engine B rejects heat to a cold reservoir. So this is 4.4 degrees Celsius or 277.4 Kelvin. So this would be Q2. If the work output of A is twice that of B, find the intermediate temperature between A and B, the efficiency of each engine, and see the heat rejected to the cold sink. So we can say the intermediate reservoir is maintained at a temperature Ti. Now we have been told that work output of heat engine A is twice that of work output of B. So WA is equal to 2 times of WB. So WA is QA minus QI. This is equal to 2 times of work output of B, which is I would write this as QI, and QI directly goes to the second heat engine B. So work output of B is QI minus QB. Okay, it's better I write it as QA and QB. So now we can solve this expression again from Carnot theorem. We have QA by TA is equal to QI by TI. This is for the first heat engine, and for the second heat engine we have QI by TI is equal to QB by TB. So solving this expression, I have QA plus 2QB is equal to 3QI. From this expression I can calculate QA. QA is QI into TA by TI. TA is 694 Kelvin, so this is into 694 divided by TI. Similarly, QB can be calculated, which is 277.4 into QI by TI. So substituting the values of QA and QB in this equation, I will have QI by TI into 694 plus 2 into 277.4 QI by TI is equal to 3QI. So I can divide the whole equation by QI, then multiply with TI, then I would get 694 plus 2 into 277.4 is equal to 3 TI. So this means TI is equal to 416.26 Kelvin. In terms of degree Celsius, it is 143.26 degrees Celsius. Now we have calculated the intermediate temperature. Now we have to calculate the efficiency of each engine and the heat rejected to the cold sink. Efficiency, now we have the temperature, we can calculate the efficiency easily. So efficiency of A is equal to 1 minus TI by TA, which is 1 minus (416.26) divided by 694. So this comes to be 40%. Similarly, efficiency of heat engine B is 1 minus TB by TI. So TB is 277.4 and TI is 416.26 Kelvin. So this is 33.36%. So efficiency is also calculated. Now we can calculate the heat rejected to the cold sink. So to calculate this, we can make use of this expression. we had QA by TA is equal to QI by TI for the first heat engine, and for the heat engine B we had QI by TI is equal to QB by TB. So now this combining these two expressions, we will have QA by TA is equal to QB by TB, so which implies QB is equal to TB by TA into QA. So QA is given in the problem as 200 kilojoules. So this is TB is 277.4 divided by QA 694 into 200 kilojoules. So QB can be calculated. So this is 79.94 kilojoules. I hope this problem is clear. If not, you can please unmute yourself and ask the doubts if you have. Mr. Sabu, is the problem clear to you? Okay. Moving on, we have the third problem here. A piston cylinder device contains a liquid vapor mixture of water at 300 Kelvin. During a constant pressure process, 750 kJ of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the water during this process. So we have a water vapor system at constant temperature while 750 kilojoules of heat is transferred, and we need to calculate the entropy. So we know entropy change is given by integral dq by t. So here dq, since this process happens at constant temperature and pressure, we can write this as del q by t, which is del q is 750 kilojoules divided by T temperature is 300 Kelvin for this process. So we have 750 by 300, which is 2.5 kilojoule per kg Kelvin. Sorry, it is not per kg, Kelvin. So this is the entropy change of the system during the process. Now in the next problem, we have 1 kg of water at 273 Kelvin which is brought into contact with the heat reservoir at 373 Kelvin. When the water has reached 373 Kelvin, find the entropy change of the water of the heat reservoir and of the universe. So this is the first part of the problem, and in the second part we have water is heated from 273 Kelvin to 373 Kelvin by first bringing it in contact with the reservoir at 323 Kelvin and then with the reservoir at 373 Kelvin. What will be the entropy change of the universe be? And then we have to explain how water might be heated from 273 to Kelvin to 373 Kelvin with almost no change in entropy of the universe. So in the first part we have water body initially at 273 Kelvin and which is heats up to 373 Kelvin. This is done by bringing a reservoir. The temperature of the reservoir is 373 Kelvin. So heat is transferred from the reservoir to the water. So in this case, finding the entropy change of the water, entropy change delta S is given by integral del Q by T. Here del Q is given by mc into dt. So it is mc dt by temperature over the integral. Now we can assume mc to be constant, so it becomes mc into dt by t. So m is given as 1, and this again while integrating we will get, say this is T1, or I would T1, I would directly write the temperature here, which is from 273 Kelvin to 373 Kelvin. So this becomes mc into ln of T2 by T1 from 273 to 373. So m is 1, it's given as 1 kg of water, and C for water is 4.187 kilojoule per kg Kelvin. So then we write the value of C, 4.187 into ln of 373 by 273. So this is 1.307 kilojoule per Kelvin. Since we have multiplied with mass, we don't have kg in the denominator. So this delta S is for the system. Now we can calculate the entropy change for the reservoir. Delta S for the reservoir is equal to, again, integral del Q by T, and here del Q has to be calculated, and T was constant throughout the process, which is 373 Kelvin. So we can directly take it as del Q by T, and here del Q is calculated as mc delta T, which is 1 into 4.187 into delta T is 373 minus 273 Kelvin. So we will have 418.7 kilojoules. So 418.7 kilojoules of heat is transferred from the reservoir. So we can write entropy change for the reservoir. So this is 418.7 divided by temperature. So temperature of the reservoir was 373 Kelvin. So which becomes 1.122 kilojoules per Kelvin. Now we know that heat is transferred from the reservoir to the water, so the entropy of the water increases, whereas the entropy of the reservoir decreases. So we can write in the proper sign convention, we have minus del Q by T. So this is minus, and we have minus here. Now calculating the entropy change of the entire universe, we have delta S of the system plus change in entropy of the reservoir. So this becomes 1.307 minus 1.122, which is for the reservoir, So this is 0.185 kilojoule per Kelvin. So this much of entropy of the universe is increased. So this is first part of the problem, where we had only one thermal reservoir. In the second part, we had intermediate. We had two thermal reservoirs. So one at 323 Kelvin and second at 373 Kelvin. So first the water is heated from 273 to 323 using 323 Kelvin reservoir, and then from 323 to 373 using the higher temperature reservoir. So just to draw the schematic, we had water at 273 Kelvin. So this is a closed system. Sorry, this is a system, and then we had a T reservoir 1 at 323 Kelvin. So heat is transferred from the reservoir to the water system. That would be, say, Q1, and then this becomes finally it became 323 Kelvin, and then next we had a second thermal reservoir T2 at 373 Kelvin, and this transferred heat Q2 to the water system, and it heated the water system from 323 Kelvin to 373 Kelvin. So now we can calculate what is the entropy change of the universe. Okay, so again we have to calculate the system change in entropy and change in entropy of the reservoir, and then we can calculate the change in entropy of the universe. So to calculate the change in entropy of the system, it is again the same, because the entropy of the system is a point function. So it depends only upon the initial and the final temperatures. So if I have to write the entropy change of the system, we have it happens in two stages. So we have del Q by T 273 to 323 plus del Q by T starting from 323 to 373 Kelvin. So if we calculate this, we will get the same change in entropy of the system as the previous case, which is 1.307 kilojoule per Kelvin. And now we can calculate the change in entropy of the reservoir 1 and 2. For reservoir 1, we had del Q by T, and here the heat transfer is only from 273 Kelvin to 323 Kelvin, and the temperature is also only 323 Kelvin. So to calculate del Q, I would say del Q1, which is mc delta T. So m is 1, c is 4.187 into temperature. Initial temperature, the final temperature is 323 Kelvin for the first thermal reservoir, and initial temperature is 273 Kelvin. So solving this, we have 209.35 kilojoules. So calculating the entropy change for the first reservoir, we have del Q by T1 or TR1. So del Q is 209.35 divided by TR1 is 323 Kelvin. So I can calculate this. So this is 0.648 kilojoule per Kelvin. Again, write in the expression, write in the correct sign convention. Since the thermal reservoir is losing heat to the water, the change in entropy will be decreasing, so we will have a negative sign here. Write this del Q as negative and this S2 as negative. Similarly, we can calculate the change in entropy for the reservoir 2. So delta S for reservoir 2 is again integral del Q2 by T2. So this is since it is happening at a constant temperature, I can directly integrate this as del Q2 by T2. Here the Q1 and Q2 is same because instead of transferring 100 degrees Celsius 100 degrees directly, we are doing it in steps of 50. So heat transfer to raise the temperature of the water from 323 Kelvin 273 Kelvin to 323 Kelvin, which is 50 Kelvin difference, is same as of 323 Kelvin to 373 Kelvin, which is also again 50 Kelvin. So I can write this del Q2 as 209.35 and T2 is 373 Kelvin. So this is 0.561 kilojoule per Kelvin. Again, for the proper sign units, we have negative here because reservoir is losing heat to the water system. Now calculating the change in entropy of the universe, we have change in entropy of the system plus change in entropy of the reservoir 1 plus change in entropy of the reservoir 2. Adding this up, we had change in entropy of the system as 1.307 minus, for the reservoir 1 it was 0.648 and for the reservoir 2 we had 0.561. So this becomes 0.098 kilojoule per Kelvin. So this is the change in entropy of the universe. Now if we compare this with the initial case where we had only one thermal reservoir at 373 Kelvin, that was 0.185 kilojoule per Kelvin, and now it has become 0.098. So it has almost become half of it. So that means when we have more and more thermal reservoirs at different intermediate temperatures and we transfer the heat and then we heat up the water system, we will have lower entropy generation. So that means we are reducing the finite difference in the heat transfer process. So when we have zero delta T during heat transfer, we will approach zero entropy generation. So that is the explanation asked in the third part of the problem. So how do we heat the water from 273 Kelvin to 373 Kelvin with almost no change in entropy? So that means I can have initially the water is at 273 Kelvin. Now I can have a thermal reservoir TR1 at 274 Kelvin, and then I bring the water to 274 Kelvin, and then in the next stage I should have another thermal reservoir at 275 Kelvin. So now using the difference in temperature of the water system and the reservoir system is only 1 Kelvin. So in the first case we had the difference to be 100 Kelvin, and second system we had only 50 Kelvin difference between the reservoir and the water system. Now if we have very less temperature difference of say 1 Kelvin, the entropy generation will be much lower than the previous cases. And similarly, instead of this 273 instead of 274, I can also have 273.01 Kelvin. Then I should have like 10,000 reservoirs, and then I can transfer the heat. But this is practically not possible, but just for theoretical knowledge, this is fine. I mean, this is good to understand. So if you have a very low temperature difference between the reservoir and the system, then and heat is transferred, there will be less and less entropy that is generated. If you have any questions, you can ask now about this problem or the previous problems. You can ask questions by unmuting yourself or writing in the chat window. Okay, if there are no questions, I will move on to the next problem. 1 kg of ice at minus 5 degrees Celsius is exposed to the atmosphere, which is at 20 degrees Celsius. The ice melts and comes to a thermal equilibrium with the atmosphere. Determine the entropy increase of the universe. Then what is the minimum amount of work necessary to convert the water back to ice at minus 5 degrees Celsius? Cp of the ice is given to be 2.093 kilojoule per kg Kelvin, and the latent heat of fusion of ice is also given to be 333.3 kilojoule per kg. So now we have a ice system at minus 5 degrees Celsius. And this is brought to this is exposed to atmosphere at 20 degrees Celsius. The atmosphere is 20 degrees Celsius, and then finally the ice has become water at 20 degrees Celsius. So initially it is at solid phase. So during solid phase there is a heat Cp of the ice is given, and then there is a latent heat of fusion at 0 degrees Celsius, where the at 0 degrees Celsius the phase change happens from ice to water, and then from 0 degree water to 20 degrees Celsius water, again some more heat has to be supplied to brought to this state. So we can calculate the total heat transfer. So total heat transfer is, we have 1 kg of ice, so mCp of ice and this temperature difference is from to a final state is 0 degree ice to the initial state of 5 degree ice. So difference is 0 minus of minus 5 plus latent heat of fusion, so that is m into I would write latent heat, which is 333.3 kilojoule per kg, plus m into C of water for a final temperature of 20 degrees Celsius from an initial temperature of 0 degrees Celsius. So calculating this, we have all m as 1 kg, so you can neglect that. Cp of ice is given as 2.093 into 5 plus 333.3 plus C of water is 4.187 into 20. So total heat transfer is known. So this is 427.5 kilojoules. Now we need to calculate the entropy increase of the universe. So that means we need to calculate the entropy increase of the system, ice water system, and then the atmosphere, and then add both of them. So to calculate the entropy increase of the atmosphere, to calculate this entropy increase of the atmosphere, it is fairly simple. We have atmosphere is equal to integral del Q by T. So atmosphere is staying at a constant temperature of 20 degrees Celsius or 293 Kelvin. So we have delta Q by temperature, and here the atmosphere is losing heat to the ice water system, so I would write, so the entropy will decrease, so I would write minus del Q by T, which is minus of 427.5 divided by the constant temperature of 293 Kelvin. So this becomes 1.459 minus kilojoule per Kelvin. So since system has only 1 kg, it is kilojoule per Kelvin. Then we can calculate the entropy increase of the ice water system. So I would write system for the first state where it becomes 0 degree ice from minus 5 degree ice. So we have the integral del Q by T. So this is mc dt by T. Here m and c are constant, so I will take it out. M is 1, so it is 1 into c is c of the ice is given in the problem, which is 2.093 into integral of dt by T from minus 5 degrees Celsius to 0 degrees Celsius. 0 degrees Celsius is 273 Kelvin and minus 5 is 268 Kelvin. Hello, sorry Prakash Kumar, I don't understand Hindi. Can you comment in English? You wanted the PDF to be uploaded, it will be, or your question is something different? So if your question is if you will get the PDF will be uploaded to a Google Drive and the link will be shared to you in the NPTEL portal. So you can log into your NPTEL portal and look for this PDF, and also the video will also be uploaded to YouTube and the link will also be available in the NPTEL portal. And I think you should in the week section, in the left pane you will have week 1, week 2, week 3 as a menu, and in the last thing I think there will be problem solving session. If you click that, it will be, you can see the link for the Google Drive where there are different links for all the week PDF and the videos. I hope this is your question. If not, you can ask me again in English. Back to the problem, we had the integration dt by t. So this is ln of temperature. So this is 2.093 into ln of T2 by T1 within the limits 268 to 273. So we have 2.093 into ln of 273 by 268. This is 0.0387 kilojoule per Kelvin. Now in the next phase we had the phase change from ice to water. So we have again integral del Q by T. Here the temperature is constant and the heat transferred is the latent heat of fusion, that is 333.3 kilojoules, divided by temperature of 0 degree Kelvin, 0 degree Celsius, which is 273 Kelvin. So this entropy increase is 1.221 kilojoule per Kelvin. In the third phase, we had a heat transfer from 0 degree water to 20 degree Celsius water. So again that will be mc into ln of T2 by T1. Here m is 1, c is 4.187 for the water, and ln of T2 by T1 final temperature is 20 degrees Celsius, which is 293 Kelvin, divided by T1 is initial temperature, which is 273 Kelvin or 0 degrees Celsius water. So this becomes 0.296 kilojoule per Kelvin. So now the total entropy increase of the system is entropy increase for all the individual process. So this is 0.0387 plus 1.221 plus 0.296. So this becomes 1.55 kilojoule per Kelvin. So now we have calculated the entropy increase of the system for the entire process, and we have earlier calculated the entropy increase of the atmosphere, which is minus 1.459. So now we can calculate the entropy increase of the universe, which is entropy increase of atmosphere plus entropy increase of system. So this is minus 1.459 plus 1.555. So this is 0.096 kilojoule per Kelvin. So this is the entropy increase of the universe in the process. Now we need to calculate how much of energy, how much is the minimum work that is necessary to convert the water at 20 degrees Celsius back to ice at minus 5 degrees Celsius. So for this we can use a reversible refrigeration system. So now we have a system of water at 20 degrees Celsius, and this has to be converted to ice at minus 5 degrees Celsius. So for doing this process we will have temperature change from 20 degrees Celsius to 0 degrees Celsius, and during 0 degrees Celsius there is some phase change. So this is 0 degree water from 20 degree water to 0 degree water, and then 0 degree water to 0 degree ice. During this we have latent heat of fusion, and then we should cool it down to minus 5 degree ice. So there are different temperature change, and so we need to use different refrigeration system, and we need to calculate the minimum work. So instead of going through all this, we can calculate in another way, where we say so this is atmosphere. The refrigeration system takes heat from the water ice system and pump it to the atmosphere. During this process, some work has to be done to the refrigeration system. So now this is Q and say this is QH. So now during this refrigeration system, we can calculate the entropy increase in the atmosphere. So that will be QH plus W min divided by the temperature of the atmosphere, that is T ATM. And we know the change in entropy of the system, which is already calculated as 1.555. Yeah, 1.555. Sorry, this QH, sorry, so this is QH, which is W min plus Q. So we had only Q here. And yeah, so delta S of the universe is equal to, during this refrigeration system also, delta S of the universe is delta S of the system plus delta S of the atmosphere. So now for the minimum work to be done, we know that there shouldn't be any entropy increase in the universe, so this becomes 0. For the system, we will be losing heat from the system, so that will be minus 1.555 as a change in entropy, plus delta S of the atmosphere, which is Q plus W min at atmospheric temperature of 293 Kelvin. So this should be equal to 0. So which implies, if we know the Q value of Q, we can calculate W min. Q value is already calculated, which is 427.5. So we have 427.5 plus W min divided by 293 is equal to 1.555, which implies W min can be calculated from this. So this is 28.115 kilojoules. So if we operate a reversible refrigeration system, this is the minimum work of 28 kilojoules has to be provided to convert the water at 20 degrees Celsius back to ice at minus 5 degrees Celsius. I hope this problem is clear. Otherwise you can ask in chat window, or you can unmute and ask your question. Okay, I hope there are no questions about the problem. Moving on to the next problem, we have we have a car engine where air is compressed from 22 degrees Celsius and 95 kilopascal in a reversible and adiabatic manner, and the compression ratio of the engine V1 by V2 is given as 8, and we have to determine the final temperature of air. So when it is a reversible and adiabatic, and if it is only air, we know that PV power 1.4 is equal to constant, so which implies P1 V1 power 1.4 is equal to P2 V2 power 1.4. So we know, okay, so from here we can calculate P2, which is P1 into V1 by V2 power 1.4. Here V1 by V2 is given and P is also given. P is 95 kilopascal into V is V1 by V2 ratio is 8 power 1.4. So we can calculate the final pressure. So that is 1746 kilopascal. Yeah. Now we can we have to calculate the final temperature. So to calculate the final temperature, we can use the PV equal to MRT relation. So here we know the we don't know the M and R of the R is known, but M is not known for the system. So we can write this expression as PV power by T is equal to MR, which is constant during the compression process. So this becomes P1 V1 by T1 is equal to P2 V2 by T2. So from here you can calculate T2 as P2 V2 by P1 V1 into T1. So I can write this expression. So here P2 is 1746 divided by P1 is 95 kilopascal into V2 by V1. We know V1 by V2 is 8, so this is 1 by 8 into initial temperature of T1 is 22 degrees Celsius, which means it is 295 Kelvin. So here we have 295. So here we have 677.72 Kelvin. So this is the final temperature after compression. We have few more problems, but we are already out of time, so we would conclude the session now unless you have any questions. Okay, if there are no questions, we will close the session. Thank you for attending. As I said, the PDF will be uploaded to a Google Drive, and the video will be uploaded to YouTube, and both the links will be available in your NPTEL portal. You can log in and see anytime, and if you have any further questions, you can also ask in the discussion forum. And if you mention that you have questions related to week 10 or any week's problem solving session, I will be able to answer your questions in the forum. Thank you for joining. I will close the call now. Thank you.